Hello everyone and welcome back to another video. Today we have a nice Daniel Rosado integral that we're going to be complex analysising. So yeah, his video on this will be down in the description. But in the meantime, let's get complex analysising, shall we? We're just going to be integrating over this contour right here. So just kind of the standard semicircular contour. Oh, that looks like a parabola. Standard semicircular contour like this. And you'll notice that our only pull here is really just going to be at x equals I by virtue of this little bit right here. Then we can just kind of factor as x plus I squared times x minus I squared, meaning that, well, just look at our contour, look at where look at our denominator. You'll see that that's really our only pull, but it has a multiplicity of 2, so we will kind of have to take a derivative. So that's I right there. So yeah, by the residue theorem then, we just have the integral, our closed line integral, is just going to be equal to, well, our actual integral here, which is going to be equal to 2 pi I times some of our residues, but we need to care about the residue, our only residue really, is the residue at I itself. So yes, now when I do write this, I should mention that when referring to I here, I really am referring to the integral from 0 to, integral over all real numbers really, of, x squared plus 1 squared still, but I'm just going to write it as e to the x minus 1 over xi dx, and then we're just going to take the real part of this entire thing. It's going to give us the same result, and it's effectively the same, just one slight caveat just to make things slightly easier on us. So yeah, all we have to do is find the residues of a residue of this integrand right here at x equals I. So let's get cracking, shall we? What we're going to do then is, by the residue theorem, we have this our residue is going to be equal to the derivative with respect to x of x squared times e to the x minus 1 over x I over x plus I squared. And that's just because we're multiplying by x minus I squared on the numerator, just by the formula, so that we can actually calculate the residues and we don't get nasty zero things. So all you have to do now is actually calculate this derivative right here, which looks, not like the most fun thing in the world, but let's get to sing the quotient rule song, or I'll sort of sing it, I guess. I don't know if I want me singing on YouTube. Anyway, we have low d high, so low, so x plus I. Oh, this is evaluated at x equals I, by the way, I should mention. Low, then d high. So then d high is just going to be, we have to kind of product rule that. So we're going to have 2x times e to the x minus 1 over xi. And then, just reverse that. So x squared times, both the derivative of e to the x minus 1 over xi. You just have to take the derivative of that bit right there. So it's just 1 plus 1 over x squared times I times e to the x minus 1 over x times I. So that's the low d high. And now we need minus high x squared times e to the x minus 1 over xi. Oh my goodness, it's getting long, but just trust me, it simplifies into something nice. X squared e to the x minus 1 over xi, d low, so that's just going to be times 2x plus I. And then square the one that's down below, x plus I, x plus I to the 4th. And this is kind of nasty right here, but let's just note a couple of things over to the right to make this simplification process a little bit easier. And this is really that if we're plugging in I here, you'll notice we have a lot of expressions of x minus 1 over x. But let's just kind of think about what this is. If we're plugging in I, you have I minus 1 over I, but we know that 1 over I is just equal to negative I, meaning that this right here is just equal to 2I. So we can kind of plug that in everywhere where we see an x minus 1 over x. So, yes. I'm just going to go left to right, start plugging stuff in. So we have 2I squared, meaning we just have a negative 4 here, times our 2I, and then e to the minus 2, and that just comes from the fact that we have a 2i times an I plus, let's take a look at this bit right here. So 1 plus 1 over x squared. So if we have 1 plus 1 over x squared here, we're plugging in I, we have 1 plus 1 over negative 1, which is just 0. Meaning, this is actually really nice. We don't have to plug in any of this other stuff. That whole term right there, it's just 0. Poof, gone. Isn't that nice? Stuff cancels. Anyway, so we have negative 4 times 2i e to the negative 2, and then we just need to do this next one. So we have minus x squared, so minus I squared, so that's just going to be plus. And then I'm going to do this bit right here next. I'm just going to have plus 4i times e to the minus 2 again, divided by 2i to the 4, which is going to be, what's that, I believe 16? Yeah, because I to the 4th is just 1. So this right here is just equal to our residue at I. Meaning that if our integral is just equal to 2 pi I times our residue, then our integral is just equal to 2 pi I. And then I'm going to simplify this right here a tiny bit more. I'm just going to, well, first thing I'm going to do is actually, before I plug it into the 2 pi, I'm just going to cancel out the 4's real quick. So we're going to have, and I'm also going to factor out e. So what we're really going to have is a 4e squared on the bottom, and on the top we're just going to have a minus 2i plus I believe. Yes. And this right here is just equal to, well, it's by addition, negative I over 4e squared. So if this is just equal to negative I times negative I over 4e squared, then our result is nothing but, well, I times negative I, that's just 1, meaning that we have 2 pi over e squared, 4e squared, and to simplify that a tiny bit more, we end up getting pi over 2e squared, which is our answer. So yeah, just some kind of light complex analysis for you today. Please check out Daniel Rosato's video down in the description, and I hope all y'all enjoyed, and I'll see you on the next one. Adios!